Hello and welcome to this presentation. My name is Vijay Jasankar and my roll number is IMT2019525. This presentation is a supplement to the slides submitted for the RL assignment 2. So in this presentation, we are going to be looking at the key ideas behind this paper, which is titled Learning to Walk in Minutes Using Massively Parallel Deep RL. And this is by Nikita Rudin, David Hoyler, Philip Reist, and Marco Hutter. So as you can see in this GIF here, which is a screen grab from their video, we can see multiple robots, or in this case, thousands of robots learning to walk in parallel in a shared environment. So let's see some of the dynamics behind how they were trained and some of the results as well. First is that RL is used in robotics quite a lot. We have seen some examples in class as well. And the paper notes that leg locomotion, manipulation, and navigation are some of the key focus areas of papers discussing RL and robotics. However, one of the key issues is that deep RL takes a long time to train, mostly because of hyperparameter tuning and so on. And that training methodology has to be changed, which is where these people come in. So the task which is in hand is learning to walk across challenging terrain, such as maybe uneven surfaces, slopes, and obstacles, while taking into account base heading and linear velocity commands from for actions. So there are two main parts of such a system. One is data collection, such as getting the observations and estimating the rewards and so on, and policy update, which is back propagation in a deep RL network. So historically, the former has been done on the CPU, while the second one is being done on the GPU. And this was what is causing the bottleneck in most of these systems, which is taking a long time to train. What Nikita Rudin and the other authors have proposed through this paper is you can do both of them online on a GPU, um, and we can do on policy networks in a very quick way, which increases the throughputs as well, which here it's measured as number of robots simulated in parallel. So one of the optimizations that they have is the shared mesh optimization, which basically means that there is only one mesh and the robots are moved from place to place. So there is many other mesh optimization techniques which I use in this paper. So the modified adaptive PPO, so as you can see here is the pseudocode for a PPO adaptive KR penalty, where we have the theta k plus 1 update policy theta k, you check the divergence, and based on that you change the update step, and you also have a clipping mechanism here. There are some hyperparameters which are very important. As you can see, they have been detailed here. Two of which are batch size, so which involves the number of robots and the number of steps. Here, batch size is taken as the product, so we can see there will be a trade-off. If you want to keep the batch size as optimal, then if you increase number of robots, you have to decrease number of steps. However, yeah, but the rewards for multiple trajectory steps are used in this advantage calculation, which is here. But that brings up another issue, which is when using the critic in an actor critic method, which uses implicit time. When you decrease the number of steps, that estimation can become very foggy. So when you take into account that the authors have proposed timeout as a kind of reset handling mechanism, then the critic network can give very shoddy estimates. So the way they have solved this is through bootstrapping, where they augmented the reward of the expected infinite sum of the critic with its own prediction, and this was proven to be a pretty decent step because it gave decent results at the end. Another thing is they used something known as this generalized advantage estimation, and that is where this batch size part comes in as well. So that is more of the PPA modifications. Now let's look at the tasks itself and some of the results. So there are many intricacies in such a task. As you can see from the GIF itself, it was quite a complicated situation. So what they have is something known as adaptive difficulty. This is used to measure how the robots are learning through time. So there are many techniques which have been proposed in the literature, but this was the most optimal one, or at least at the time. So the way it works is the mesh is organized into progressively increasing complexity zones. So for example, you could have just a flat surface in the first zone, and then you could have stairs in the third zone. And instead of shifting robots from zone to zone, they shift them from point to point in that zone itself. So, for example, you can see here there's flat, sloped, randomly rough, discrete obstacles and stairs. These could represent different complexities. There's no need for tuning again. And you have a current progress distributions. That is, at one point of time, when you measure the state space, you can see certain robots are in the flat zone, for example, and certain robots are in the stair zone. So we can see the performance of the policy through this distribution. And this makes it very elegant because you do not need to hardcode that in. Next, you have the information and reward. So what they authors have said is that the robot will sense proprioceptive measurements, The definition of which is basically measurements about self movement and self locomotion. And what this entails is things like angular velocity, measurement of the gravity vector, joint positions, and so on. Next, you have the reward, which is a weighted sum of these terms. As you can see here, linear velocity tracking, angular velocity tracking, joint motion, action rate, and so on. So it's a weighted sum of these. And along with this, there are also some additional penalties imposed for actions that look quote unquote not very aesthetic. So when you see robots walking, if they take very small steps, it might look a little bit weird. So longer steps are valued more, and you also have smoother motion. So this terms for those as well. Next are the actions itself. So you manifest these through desired joint positions. So you tell the robot these are desired joint positions, and the motors and the servos will take it to that particular position. And to simulate reality, which is in tune with the sim to real paradigm, which are used in robotics papers, they've added friction and some randomness in the environment dynamics and a network to estimate that triggering motion of you tell the joint positions and it will move it to that. And one marked difference from the other systems is that it uses an LSTM instead of just a CNN or just feed forward neural network here. There is also something known as acceptance testing. This doesn't, of course, fall only in actions, but at the end of it, they look at robustness and the traversability of this robot. So this is also part of the sim to real paradigm, where it is pretty important for a robot to be robust and traversable in the real world. Let's now look at some of the results, and we'll also look at what is this S2R fine tuning, which I will come to in a second. So as you can see in this graph, we can see something that might look a little bit counterintuitive. That is, when you increase the number of robots, the performance is actually getting better. And let's look over to the batches later. But if you see the second graph here, if you increase the number of robots, the training time decreases, and we're talking about the order of 10 to 15 minutes here. And the reason is, as we saw, the trade-off, right? So if you increase the number of robots, the temporal aspect becomes much lesser, and that is the bottleneck, because the information collection part, even though on the GPU was the bottleneck, so it trains faster. However, it must be taken into account that even the batch size has a slight issue. That is, if you increase the batch size or if you decrease the batch size, you have different performances. As you can see over here in this graph, you can see that the final reward was in a batch size of around 100,000 to 200,000. And in fact, this was also echoed in the paper as well, where they took 4,096 robots with a batch size of around 100,000. So then we also have bootstrapping, as alluded to earlier with the actor-critic discussion. With bootstrapping, we can see that there's a marked decrease in the critic loss as compared to without, where it gets very hazy due to the lack of implicit time and the early stopping, so to speak, with the timeout mechanism for resets. We can see that the reward is also increased and the critic loss is also quite lesser as compared to the without bootstrapping case. So this is something I found interesting. And there's also, this is the distribution of the processing time. So you can see that simulation was the bulk, actuator network, which was to tell the robot these are the joint positions, you should move the servers accordingly, was a yellow, and observations reward was green, and inference was red. As you can see, blue is still dominating. However, this is a lot better than using the CPU, because the CPU, if in the CPU case, this bar would be a lot bigger in terms of proportions. So this is also including the learning part, which is the back propagation again done on GPU. Now coming to S2R fine tuning, like we mentioned, S2R basically means simulation to like reality. So if you were to use it in a real robot, the results were not as good as in the simulation, which we saw earlier. So what the authors propose is that we should do something known as reward tampering or reward training. Even though it was going to a trotting gait, as in like when the robot was trotting, like how some animals do, they had sometimes dangling legs, or some joints were very awkwardly put to ensure that they actually move. And to avoid that, they had to tweak the loss function, where a decrease in robustness asked them to change the reward function to penalize these anomalous movements. And lastly, they also say that there's something known as a teacher-student paradigm, which have been used in other papers as well, which could augment this for the real-time or real-world cases, and this would show marked improvements, and this represents the future work. So, in conclusion, in this paper, they had showed that you can use the GPU for many interesting things, and more specifically, you can very efficiently and rapidly parallelize all of these operations. And by modifying PPO in not too complex ways and to reduce the decision surface space, you can still get very good performance with a lot more throughput than other methods. And what the author says that this could represent the frontier in reinforcement learning research for robotics, where other researchers can use their framework and use their methods to train theirs and get quick results. So we're talking in the order of 10 to 15 minutes for quite a large batches and quite a lot of robots. So this can be used for very good experimentation. So that concludes the presentation. Thank you for listening.